In this, we're going to study one of the very important convergence test called the direct comparison test. The direct comparison test. Direct comparison test, what we normally call DCT. Before we go to the direct comparison test, we need to kind of recall one of the very important result that is called the P series. P series, pretty much the P series test. So what's a P series test is, we have sigma n going from 1 to infinity, 1 over n to the p. We know that this series gonna converge if this is going to converge if p greater than 1. This series going to diverge if p less than or equal to 1. So if you kind of draw it, so that's the situation. So we're going to see 1 here. So it says that, so if we have open 1 to infinity, the series going to converge. The other side series going to diverge. So that going to help you. So it's 1 over is gonna converge. Okay, so this is one of the very important kind of auxiliary result that we're gonna use throughout this. I mean, most of the time we're gonna use that. So let's go to the theorem. So what the theorem is about? So this is the DCT, direct comparison test. So we're gonna get, so suppose, so we have two series. Suppose sigma n and a sigma bn are a series with positive terms. So that's one of the requirement. Those terms will be positive requirement, and we have this important condition. So 0 less than or equal to an, less than or equal to bn. I'm gonna say eventually. It's not like really mathematical way to say it, but let's write it like this. Easy to remember. Eventually, that means after some time, this gonna be the case. So after some n, this gonna be a 0 less than a 0 less than or equal to n, less than or equal to bn. So that means we can ignore first million or billion terms that does not follow this pattern, but after that it should satisfy this condition. So it's very, very important. So that means the terms of the an series has to be less than or equal to the terms of the bn series. So if that is the case, there are two results. So the first one is, if the larger one gonna converge, then the smaller one has to converge. Smaller as n has to converge. And then the other one, if the smaller one diverges, then the larger one has to diverge. So you can see that these are kind of obvious result, but there are a lot of applications of this one. So I want to warn you here. So if the larger one diverge, it doesn't say anything about the divergence of, if the larger one diverge, it doesn't say anything about the divergence or convergence of the smaller one. So so I should say does not say anything. So does not say anything. So does not say anything about the convergence of the smaller one. And the same way, if the smaller one converge, then it does not say anything about, so it does not imply the convergence of convergence of the larger one. So you can see that, so you have to be very careful with that. So it does not follow anything about that. So it's only say if the larger one converge, the smaller one converge. If the larger one, if the smaller one diverge, the larger one diverge. That's the only way it's gonna go. So let's look at some of the interesting examples here. Remember, this is just a review. If you need to know like more about it, you need to go to the main lecture and then try to learn from there. So this is just a review, only important facts. So test for convergence. Test for convergence. Test for convergence. So let's say the first one, sigma n going from 1 to infinity, 1 over n squared plus 1. So if you get a series like that, what are you gonna know? We need to kind of compare this with something else. So the question is, most of the time, how do you know what? Because you know that you try to kind of show that this is gonna converge. Actually, yeah, that's the part actually we don't know. So what we're trying to do is, because we're trying to show that, look at the dominating terms. When you look at the dominating terms, it's kind of suggest a series. So if you look at the dominating term of the numerator, it is 1. If you look at the dominating term of the denominator, it is n squared. So that means we're gonna compare this with this series. We're gonna compare this one with just picking the dominating term. You're gonna compare this with 1 over n squared. It's kind of suggests that. Now, fortunately, what's gonna happen? So in this case, so we have an, which is 1 over n squared plus 1, and we have bn, which is 1 over n squared. So then what we know that then what's gonna happen? 1 over n squared plus 1 is less than or equal 1 over n squared for n greater than or equal, because when you add something to the denominator, that term is smaller, right? So that's true. But what do you know about the second series? Second series, the p series with p equal 2, that's going to converge. So that means the smaller one has to converge. So we can see, therefore, the series, therefore, we can say by, because this is an argument, therefore, by the direct comparison test, the series n going from 1 to infinity, 1 over n squared plus 1 converges since sigma n going from 1 to infinity, 1 over n squared is a converging, these words are important, converging p series with p equal 2, which is greater than 1. So that is the complete argument of the method. Okay. That's the complete argument of the method. So you can see it's like kind of very simple, not that bad. So now you can see that if you try to kind of apply this technique with this series, so if you try to apply this with this series, n going from 1 to infinity, 1 over n squared minus 1, you get stuck because it's in the backward. Because you try to show that this can converge, but 1 over n squared, when you try to compare 1 over n squared, it's going to go backward. So so it is not, so this is not true. So this is not true. So you can see that this is not true. So that means if you try to use the direct comparison test for this, it's not going to work. Okay? It's not going to work. So we need the other one. Okay, so that's about that. So let's look at another one. So that's the next example. So this is B. So let's try to do this one. Sigma n going from 1 to infinity, log n over n. Now when you try to look at this series, you don't really see like much connection here unless you try to kind of look for certain things. So let's consider the graph of y equal ln x. Why we look at the graph? It's easy, but if you know the actual argument, then you find. So let's look at the graph of this one. What's the graph of this? So you can see that there's a natural log, so it has a graph like that. So that means that is a 1, and then you know that at e, which is roughly 2.718, at e we know that ln e equal 1, so you get exactly 1 here. This is the graph of ln x. So at e we know that ln e equal 1, so that means what you can say is we know that ln x is greater than 1 if x is greater than e, right? So you can say for our purpose we can say greater than 3, which is greater than e. That's what we want, so we're gonna go with that. Okay, so but it's actually is e. If it is greater than e, is greater than 1. So that means if you try to consider terms after 2, like starting with 3, that means the numerator is greater than 1. The numerator is greater than 1. So that means if you put 1, this is bigger than that. So that means now we see what we need to do. We're going to compare this with, one with 1 over n, because 1 is the smallest that you can get. Okay, but we know that the other series diverge, so this one is bigger, so that means this has to diverge. Okay, so so we can say not that ln n over n is greater than or equal 1 over n for n greater than or equal 3, because it's a series, we just go with 1, 2, 3, so that's true. But the series sigma 1 over n is a diverging p series, with p equal 1, or you can say that this is a harmonic series. This is the harmonic series, because we know that the harmonic series is diverging. We can say the harmonic series, so that's another way to say it. So this is one of them. Okay, so thus by the direct comparison test, therefore by the direct comparison test, the series n going from 1 to infinity, ln n over n diverges. Okay, so it's a simple argument, but you need to kind of understand how the ln n looks like. So this is a simple direct comparison test result. Okay, it's very easy to prove using the direct comparison test. Okay, so these are all the pieces that you need to write when you try to make an argument like that. So I'm going to give you some problems for you to try. How about this? So you can try this. See whether you can do this one. I'm going to make it upside down, n over ln n. Okay. Also try. Also you can try n going from 1 to infinity, n to the n over n factorial. Okay, so good. Okay, so let's go to the next one. So the next example, So example number 3. So C, this case. So sigma n going from 1 to infinity, 10 minus sine n over n to the 4 plus 3. Let's put square root here. Okay, something like that. So, but it looks complicated, but once you know it, you can see that this is a very simple problem actually. So we need to notice few things. First thing is, we know that there's a sign here, but what do you know about sign? Sign is always in between. So you can say first note that sign is in between 1 and negative 1. So what is the smallest value the top can have? So because sign can go to negative 1, so that means the smallest value is 9, less than or equal 10 minus sine n. What's the largest value? Is 11. So you can see that the top is in between 9 and 11. Is that right? So what's going to happen in this case? So you can replace the top by the maybe the largest value, or you can even go a little bit more. You can put 11 or 12 or whatever larger. So that means you're going to compare this with, you're going to put 12 for the top, or 11 or 13. What about the bottom? Bottom is like almost like n to the 4th square root. That means n squared. So that is the one you're going to compare. So you only look at the dominating term. So you can the largest term of the numerator and the largest term of the denominator. So from that, now you can make a comparison. Okay, so then what can happen? Then you can say that 0. We can say 10 minus sine n over n to the 4th plus 3 square root is less than or equal, if you put 12 and you are adding here, that means this is going to be smaller than n squared. If you have minus sign, we cannot make this argument, so we have to think about something else. But with the plus sign, we can do it. If we have n squared plus n squared minus 3, this is not true. Okay. So for you can see n greater than or equal 1. Okay, so we have everything we need, but we know that the second series converge. So but you can say sigma n going from 1 to infinity, 12 over n squared. Even with 12, we still call it p series because that's a constant. Is a converging p series. This word is important. Converging p series with you can say with p equal to, which is greater than 1. So therefore by the direct comparison test, sigma n going from 1 to infinity, you can just call it an, or you can actually write, if you want to do a good job, you can actually repeat it here, or just say an, and 4 plus 3 square root converge. Okay, so that's the complete argument. So it's not that difficult, but we notice something simple. Okay, now how about this one? As we just discussed before, if you try to do 1 over n squared minus 1, something like that, but we know that this series converge, and also if you look at sigma n going from 1 to infinity, 1 over n squared minus n minus 1, this one diverge, but unfortunately we cannot use the yeah, so for this one, yeah, it should be plus. So with the plus sign, so I wrote the wrong one. So if you see n plus 1, we know that this series diverge, this one converge, but in these two cases, we know that the direct comparison test does not work here. So you cannot use it the direct this kind of way. Okay, so because inequality is in the wrong direction. Good. And these are some exercise problems that you can try. So I'm going to repeat something that I mentioned earlier. So see whether you can prove n over ln n is like backward, like upside down. And also try sigma n going from 1 to infinity, n to the n over n factorial. Just try to rewrite, like, expand this and see what's going to happen, how the terms looks like. And then n going from 1 to infinity. How about n factorial over n to the n, like upside down. Okay, so think about those terms. But how about this one? So let's say you have n going from 1 to infinity, 3n over n factorial. I mean, you can try this, but this is not a really good problem for this type. So we normally don't do this kind of one. We normally use this one for the ratio test. So this is a good problem for the ratio test, and we're gonna discuss that kind of problems later. And this one also, when you have when you see factorial, we normally go with the ratio test. So you can try those two using ratio test, but the first one you can do using direct test. So maybe this one you can use the ratio test. But yeah, so both of them you can use the ratio test, but also you can use the direct comparison test for some of them. Okay, so this is the end of the direct comparison test.